Morning, everyone. So yesterday we had a look at Le Chatelier's principle. Essentially, how a system at equilibrium, if you poke at it, you stress it out somehow, we learned ways to actually predict whether we end up shifting left or shifting right to try to counteract that change. So let me just give you a quick warm-up question here. For starters, I just want you to state Le Chatelier's principle. That's what I just alluded to here. And then part 2 of this one here, I'm going to give you an example of an equilibrium system and just give you a few different pokes of the system. Let's take the equilibrium 2H2 and 2NO becomes N2 and 2H2O. The delta H of the reaction, just borrowing one from the notes package here. And what I'm going to do is I'm going to give you a bunch of different stresses. So here's the stress. And I want you to just predict for me what the shift is going to be, right? So I'm going to poke at it somehow. How does equilibrium respond? You can sort of tell me what's the consequence of that shift. Does the concentrations end up going up, going down? What happens to KEQ? Sort of like that, right? So in terms of the stresses here, let's increase temperature. So that's the first shift here. Second one here, let's decrease the NO. Let's pull down the NO. Third one, let us increase the volume of the container, and then let's add a catalyst. Right? And it's as simple as just saying shift left or shift right, and then just tell me what happens to the concentrations. Okay? I encourage you to pause the video. You can try it for yourself. In stating Le Chatelier's principle here, usually they do emphasize here when a closed system at equilibrium. Well, we know we have to be at closed system to be at equilibrium anyways, so sort of redundant there. But closed system, especially if I produce a gas, I don't want the gas to actually escape on me. When a closed system at equilibrium is stressed, when you poke at it somehow, stressed with temperature, pressure, concentration, what have you, the equilibrium is going to respond. So the system tries, or tends to, tries to counteract the stress. So the direction is always against you, right? Nature is always fighting you here. You can sort of hint to yourself, nature tries to undo what we do, although when you're stating it, you want to be a little bit more scientific. So in this picture here, we have an equilibrium system. Anytime I have the heat term just sort of on the side here, I usually just put that heat term back so that I can track my changes. This is negative, which means an exothermic reaction, which means it should be a plus 84 on the right-hand side here. Then I come along and I stress it. First one I do is I increase temperature. Yes, I increase the entire box's temperature, but I can think of the heat term as a chemical. If I increase this, I'm going to end up trying to shift away from it so that the N2 and H2O can endothermically grab some of the 84, reform my reactants to use up some of the extra heat. In this case here, it ends up shifting left. What happens to the chemicals here? The H2 and the NO, these ones here are going to go up because I'm shifting to the left. I'm forcing more products to become reactants. What happens to the N2 and the H2O? These ones here are going to go down. And I can even comment here, what happens to KEQ? Remember, temperature only changes with, KEQ only changes with temperature. I am changing temperature here. KEQ, or KC, is supposed to be products over reactants. I have a situation where as I shift, I'm actually losing products and I'm actually gaining reactants. My ratio is going to steadily get smaller as the numerator shrinks, so my Kc is actually dropped. Next one, let's decrease NO. Let's pull down the NO. As I pull down the NO, suddenly I don't have that much NO here to react anymore here. I'm going to shift left to try to replenish that. You can say shift left, or you can even say shift to reactants, just getting you familiar with the language. Again, when you shift to the left, no doubt the hydrogen is going to increase, right? As I shift to the left, same as before, I'm going to gain reactants, I'm going to lose products. That's still true. The tricky one is going to be, well, what happened to the NO? Well, a couple things have happened to the NO. If I plotted the concentration against time, just plotting the concentration of NO, at first what I did is I removed it. I pulled it down. So all of a sudden, its line went down by a lot. As I shift to the left, I'm trying to recreate the NO. I want this NO value here to steadily climb. It never climbs up to what it was before. That's where we had this notion. It tries to counteract you. It tries to bring the NO back up. But overall, compared to the initial equilibrium, I am still lower than what we begin with. The NO has actually dropped. Right? What happens to KEQ? Because this is not a temperature change here, KEQ is the same. Right? Even though all the numbers are totally different here, they've somehow changed in such a way to preserve that ratio. What if I increase the volume? What if I suddenly make the room so much larger? So if I go from a small box and I suddenly go to a much larger room, at first what's going to happen? Concentration is N over V. Suddenly being in such a big box, the concentrations of everything would drop. However, as it proceeds towards equilibrium, I have 4 moles. You can assume that they're gases. We have 3 moles total worth of gas. Because I have so much more space to spread out into, I'm going to prefer to produce the side with more moles to try to fill up some of that room. It's going to be a little bit harder for those 4 moles to actually collide in a much larger room. So therefore, the reverse reaction is predominant for a little bit here. Again, we had the shift left. And in this case here, we can talk about what happens to the concentrations. Again, at first, all the concentrations would have dropped. If I did this one in a little more detail here. Right. So I have 4 chemicals here, H2NO, N2, H2O. Right. So H2. Again, I don't know necessarily their starting amounts. That's going to depend on the temperature. That depends on how much you started with. What's going to happen here is suddenly increase the volume. You're going to get sudden jumps downwards for all of them. Boom, 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 right? All of a sudden. And then what's going to happen over time is because I have so much more room, I'm going to shift 3 moles towards the 4 mole side. The H2 and the NO are going to try to climb back upwards. They're not going to get as high as what it was to begin with. The other 2, which had already dropped, are going to keep getting lower because they're on the other side of the equation, and therefore dropping like that. So therefore, if we make a conclusion then, definitely the N2 and the H2O, which are products, those ones have just decreased. Right, that's all that's happened to them. For the other 2 here, there was the initial drop because the volume was increased. They are climbing as it tries to get closer to equilibrium, but you notice, again, it never gets back up to what it was to begin with. So in this case here, you can also say H2, a little bit more tricky there, but compared to the initial equilibrium. Let me make that note here. These ones here are compared. Let's do a different color. These ones here is compared to the initial, the starting equilibrium. Right? This just means it's lower than what it began with, even though it may have been climbing as it tried to shift. Adding a catalyst is always the easiest one here, so there's no shift. In this case here, the latter 3, I changed concentration, I changed pressure and volume, I changed catalyst here. The KEQ should be the same for all those because only temperature changes KEQ. For our lesson today, we're going to look at a few specific equilibrium reactions. We're going to study that liquid-vapor equilibrium, that physical equilibrium that we talked about earlier, and we'll talk about more of the vapor pressure later on. So first, our industrial equilibrium processes here. Let's imagine you were in the industry of making certain chemicals here. There's 3 special ones that you want to take note of. We've actually hit these ones before. So this one here is first called the Haber process. Picture of Haber there. Basically, what he was doing here around the 1800s, 1900s or so, he was trying to develop a process to directly combine our air, which is like 70-80% nitrogen and lots of hydrogen in the air anyways. He was trying to use an iron catalyst. We had saw that in chapter 3. He was in the business of trying to making ammonia. So ammonia is this NH3. So your goal is to make NH3, right? Why was this important? Here was the ammonia. So nitrogen is important for plant growth, right? So a lot of agricultural things here, but plants cannot access this nitrogen as N2. N2 is very inert. It's pretty much sticks to itself. The plants can actually harness the nitrogen. So therefore, by putting it into ammonia here, ammonia can be converted into ammonium ions and different salts, a lot more practical use. So we have a major use of NH3 in fertilizers, right? That's when the plants can actually harness this, right? So let's think about our chapter here. According to Le Chatelier's principle, which conditions will result in the highest yield, the most ammonia? And all we're going to do here is we notice ammonia is a product. If I have my choice, I want the equilibrium to shift right. I'm going to do whatever I can to temperature, to volume, to concentration, so that I can shift right. Well, what can I do? Let's do temperature first. Being an exothermic reaction, right, negative there, that means the positive 93 is on the product side. will I want hot temperatures or cold temperatures? Well, in this case here, if I pull down the temperature, I'm going to shift it clearly to the right, that's going to end up generating ammonia. So in this case here, I'm going to want relatively low temperatures. More on that in a second here. What I want in terms of concentrations. I want to do it in such a way that I have a ton of reactants, right? As I increase N2, increase H2, equilibrium doesn't like having so much reactants. It's going to shift over. It's going to try to create more ammonia. So in terms of concentration, I want to have high concentration of N2, high concentrations of hydrogen. That may just sound like, oh, more reactants means more products. Sort of, in this case. How about for pressure and volume? Being these as all gases here, I'm going from 4 moles worth of gas to 2 moles worth of gas. Do I want a lot of space or not a lot of space? In this case here, going from 4 to 2, I want to have less space, right? If I have less space, so less volume, you can do that by increasing pressure. Therefore, I'm going to convert to the side with less moles, so therefore I can end up saving space. So, in this case here, perfect. That's what we predict based on Le Chatelier's principle. We want to have the coldest temperature that we can have, the most reactants, and the smallest volume, highest pressure. Again, we're talking here in industry here. You're actually paying the bills for this as well. In general, yes, it's true. Lowering temperature would shift it to the right. But remember in our kinetics chapter, if you decrease the temperature too much, there's not enough particles that have sufficient energy. Therefore, the rate would also be slower as well. So if I have extremely low temperatures, low temperature also means slower. So it's sort of a little bit of a compromise here. I wanted to drop the temperature so it can shift right, but if I drop the temperature too much, my particles don't have the sufficient energy to get over the hill. So that's not good. Second case here is usually if I want to have a high pressure system, we're usually under just 1 bar of atmosphere in front of us here. If I'm going to have a really heavy duty container that can sustain these high pressures for long periods of time, usually having those systems is very expensive. So high pressure, usually very expensive. Right, so the chemistry is there. The chemistry says, yeah, make the pressure high, small container, so therefore I can shift towards equilibrium. But there's always a sort of a compromise that we hit. So I'm just going to list for you some optimum cases here. You don't need to memorize these values exactly, but just to highlight, even though we know the chemistry, we know we want it to shift right, there is a limitation of how low the temperature I can get, how high the pressure is. So in terms of the optimum here, usually we keep the temperature around 450 degrees. So still fairly hot, right? It's not like if I increase the temperature, let's say 1,000 degrees here, the rates are fast, but unfortunately it's shifting away from me. And it's not super cold that the rates are too minimal. So temperature roughly about 450. For the pressure, 2 times 10 to the 7 pascals. Usually 1 atmosphere is 1 times 10 to the 5. So this is about 200 times atmospheric pressure. So about 200 times the atmosphere. So it is already high pressures. Probably beyond that here is going to get very expensive. Not just for keeping the container safe, but also running it for long periods of time. I want to be in the business here for years on end to produce this ammonia here. We do want to have the catalyst here, even though catalysts here, hey, they don't shift anything here. But catalysts in general, we've been using iron as a catalyst here. Typically, the iron has a very high surface area. It's a heterogeneous catalyst. It's in a different state. It's solid, whereas the reactants are gaseous. In this case here, it'll speed things up. So speed up reactions. So you see there's a sort of difference between sort of the pure chemistry aspect. I know what I want, and then there's more, well, what if I were actually doing this here? What are some other considerations involved? Okay, so they can just say state the Haber process and then just talk about why we keep the conditions as we do. Second industrial process that we are interested in here is called the contact process. In fact, the contact process here is multiple different steps here. It's overall in the generation of sulfuric acid. Sulfuric acid is H2SO4. I want to make it from elemental sulfur through a couple steps here. So technically speaking, the contact process here is separated into 3 steps. Usually the step that we're interested in is step number 2. So sometimes if they just say state the contact process, you might be able to just state part 2 in this. So what happens here is I'm going to take elemental sulfur, S. Sometimes you see it as S8 because it actually comes as a grouping, but more often than not we just say S like this. We burn it in air, so it's going to react with oxygen. This is going to produce SO2. Right? Can't produce a CO2 and water products because I don't have a carbon or hydrogen source. So that's going to be in equilibrium, just burning SO2. Once I get the SO2, I can convert it into SO3. So what's going to happen here, this is the step that I would quote. So 2SO2 as a gas that we got from the first case here, I'm going to further oxidize it. This one here is going to be in the presence of a catalyst, another transition metal catalyst, although it's in the compound form, V2O5 as a catalyst to speed up the reaction. This converts it to form 2SO3, also as a gas. This one here, the delta H is negative 196. So thinking about the shifting here, the heat term would be on the right-hand side, so plus 196. Again, I would want relatively cold temperatures, but not too cold to make it too slow. Right? Why is this reaction so important here? What you'll realize is, again, they allude to it at the bottom here. Once you get it to this SO3, I'm going to take the SO3, which is currently a gas. It's a non-metal oxide. When non-metal oxides react with water, it's actually going to form an acidic solution, and that's where I get sulfuric acid. Sulfuric acid is usually referred to as the king of acids. I produce many millions of tons every year. So sulfuric acid has a lot of applications, manufacturing polymers. We're going to see in our organic chapter, sulfuric acid is used as a catalyst in detergents, steelmaking. That's the important use. So what I want to just sort of imply here, yes, the SO3 as a non-metal oxide, sort of plus water, it ends up generating H2SO4, sort of a little bit contributing to our acid rate problem. Even SO2 is also a non-metal oxide. In the presence of water, this one ends up forming sulfurous acid. Both of those, obviously the H2SO4 is more important, but both of those are non-metal oxides. Both of those I expect to form acidic solutions. Right? So let's do our chemistry first. According to Le Chatelier's principle, according to just the shifting stuff we talked about, which condition will have the highest yield of SO3? SO3 just means, the yield just means the producing the most amount of product. So which one, again, will shift this equilibrium shift right? Well, we just talked about here in terms of temperature, I want it to be a low temperature, not too low. In terms of concentration, I want to have lots of SO2, lots of O2. In fact, what you can actually do is you can even remove the SO3. If I can somehow set up my system that as you create SO3, I constantly keep pulling out the SO3 in the system, by removing the SO3, that's also going to shift the equilibrium to the right. That's also something you can do. In terms of pressure and volume here, we're going from 3 moles of gas over to 2 moles of gas. Again, I don't have that much room, so in this case, I might want, again, high pressures or low volumes, right? That's going to shift 3 moles to 2 moles, and then we've already talked about the vanadium catalyst here. Okay. So those are some environmental features here. It's mainly the important note for temperature, not too low or too slow, right? Or it is too slow, not too low, right? That becomes too slow. And also not too high pressure, or else it becomes too expensive. Right? So it just introduces that sort of economical aspect of this here. We may know the chemistry, but when it actually comes to actually making these, it may be a little more difficult. Right? I'll leave this next one for you to try here, the production of methanol. This mixture here of CO and H2 in our energy option is called as synthesized gas or synthesis gas. Basically, this can be used as a fuel by itself. This can produce methane. In this case here, is producing methanol. Just focus on the goal. Our job is to produce methanol. Your job is to create more products. Again, very boring here, still an exothermic reaction, so the heat term is here. So can you tell me, in terms of temperature, pressure, concentration, things like that, which one will produce my maximum yield of methanol? Right? Let's just do it on the side here. Well, in terms of a temperature, I want to have a relatively cold temperature. So we have, I want low temperatures. That's going to shift it right. Low temperature to shift right, but not too slow. Right? So it still has to have sufficient energy. Right? We're thinking about the kinetics concepts here. It needs to have sufficient energy, sufficient geometry. That's still important. Right? In terms of pressure, well, pressure, again, we're going from total of 3 moles of gas, producing 1 mole of gas. Again, we want to have less space. So what's going to happen here is we want to have relatively high pressures. High pressure can be done by doing low volume, if you can squeeze the container. Not the only way of doing it, but that's one way. High pressure preferences the forward reaction. It makes the forward reaction easier, because the forward reaction needed 3 particles to collide. The reverse reaction didn't really care, right? It's just one particle breaking up. So this is going from 3 moles of gas. We're only looking at the gaseous species. Again, sometimes the coefficients are actually matched up on both sides. In that case, there's no shift. So the actual condition, again, you don't need to memorize the exact number, but this one here is typically 10 times 10 to the 6 pascals, right? So again, normally it would be 1 times 10 to the 5, so it's 100 times more than atmosphere. Temperature here, a little bit more manageable of 250 degrees, not too cold. If it's too cold, again, the rate will be too slow. If you go too high of temperature, it's going to shift to the left, so you want that sort of nice middle ground. Even though catalyst here doesn't shift equilibrium. Why do I care about it? Well, no shift. However, it increases both rates. So in this case, this one, adding the appropriate catalyst increases the rates of reaction. Sure, you would have made the synthesis gas become methanol. The methanol will also have an easier time becoming synthesis gas, but no doubt the rates themselves are a little bit faster. So both rates faster. And usually for this catalyst here, some choices we have are copper, we can have zinc oxide, we can have alumina, which is like alumina oxide as well. You could even play around with concentration again. You could talk about increasing the carbon monoxide, increasing the hydrogen. Careful, carbon monoxide is a toxic gas, so we want to be really careful when we're designing that there. Again, because methanol is being generated, if I can slowly taper off the methanol as it gets created, that'll also further shift the equilibrium to the right. So again, just a nice, they want you to know these industrial processes, but sort of an application of from Electrotellius stuff that we talked about in shifting over to the right-hand side. Okay. So make sure you study those reactions there. We're going to do the next page here, which is also on liquid-vapor equilibria, something totally different from earlier, but just to finish off our lesson here. For liquid vapor equilibria, we are back to a physical equilibrium case. So unlike actually breaking bonds and forming bonds like earlier, this is just a physical change. We alluded to this on the very first lesson, but let's just go through in a little more detail. We're going to start off with a container. It's filled with a liquid. This liquid here, the particles are just happening to slip and slide past each other here. At any given point, liquid molecules here can evaporate, right? So I may have the lucky, really fast-moving particles. It was on a collision course with the surface. It's atmospheric pressure that's trying to keep it in the container. But maybe that lucky particle here breaches the surface tension and actually manages to vaporize, actually manages to get into the gas state. What's the difference between evaporating and boiling? Both of them refer to liquid to gas. For a boiling case here, you would have wanted to heat up the liquid enough so that all the particles have enough energy to escape. In this case here, I'm not at boiling temperature yet. I'm just having evaporated. When you evaporate it here, again, I'm going to have a closed system. I don't want these gases here to actually escape. So let's just remind ourselves, closed system. What's going to happen is eventually you're going to hit an equilibrium. Eventually, yeah, at first it was all liquid. You managed to produce a few odd gas particles because the gases couldn't escape. When the gas particles build up enough, the gases themselves are going to start colliding on the surface of the liquid. So that actually exerts a pressure called a vapor pressure. If the evaporation taking is seal pressure, the pressure grows until equilibrium is reached. It grows until you have enough particles up here that constantly is applying the same pressure. Gases are becoming liquid as the liquid is becoming a gas. So let's imagine this were water. Water is a liquid. At first, it was just pure evaporation. Just the lucky, fast-moving water particles managed to get into the gas state. The forward reaction I'm showing is evaporation. It is a physical change because it's still water. I'm just breaking those intermolecular, those hydrogen bonds there. Eventually, the gaseous particles here build up enough that they can actually recondense to form a liquid. And at that point, when they've actually hit equilibrium, the pressure at which they're actually applying is going to be referred to as vapor pressure. So at equilibrium, so I've waited for the particles to become gas, I build up more gas. As the gases start reforming liquid here, they're going to start pushing down on this liquid here. That pressure that's being exerted is called the vapor pressure. So come some key conclusions from that there. The vapor pressure is from the gas. We're going to see a conclusion if you have more gas particles at equilibrium. If you have more particles, you're going to see it actually applies a greater vapor pressure. But you have to remember that we don't measure this this can be called partial pressure at other times, but we don't measure this partial pressure until we're actually at equilibrium. What's the equilibrium between here? The equilibrium has to be between the rate of evaporation. Constantly, liquid is still jumping into the gas state, but the gas particles are also constantly jumping back into liquid state. So the rate of condensation. All right. So just some more details here. That is basically the key idea for this last section here. One note here is they're going to talk about an enthalpy of vaporization. So this is going to be a delta H. We did a lot of enthalpy changes in chapter 5 last year. In this case here, we can write down this is the energy needed to convert. There's that pesky 1 mole in our definition again. We want all these values here to be quoted per mole so that later on if I do Hess's law and I need to scale up the values here, I can scale up the value that's guaranteed for 1 mole however much I want. So energy needed to convert 1 mole. That's where we get on our tables kilojoules per mole of liquid. Right, I want to vaporize that liquid, so I'm converting that liquid into gas species. No chemical change, the bonds are still intact. Okay, so let's just think through the logic here. In order for a liquid to enter the vapor phase, the molecules on the surface need a certain amount of kinetic energy. So what's happening here is, on any given surface, we have particles, sure they're not stationary, but in water's case here, there are hydrogen bonds here that are sort of the in-between forces. On the top, they're sort of just adhesing, they sort of form this thin film. So for something to actually enter the vapor phase, they needed to be a fast-moving enough particle to actually breach this surface tension. We actually need to break off the intermolecular force. It really had to be a really fast-moving particle, just happening to be the right geometry to actually get out. So there's a minimum amount of kinetic energy, the minimum speed that these ones here have to have. It's sort of similar to activation energy, although remember it's not a chemical change, so it's not quite activation energy. Vaporization is an endothermic process, right? Because if I go from having liquid to having gas, well, gas is way more energetic. I would need to put in energy. So plus energy on this side, it's endothermic to actually get it to the gas state. So vaporization is an endothermic process. Energy that's absorbed is used to break up those attractive forces. So in this case here, they've done it for water for you. Water as a liquid and trying to become water as a gas, the delta H value is positive 40.7. Now, I know people were asking before, well, if this is endothermic, well, I'm putting heat in, but yet it's heating up as well. You have to be careful here. If I put this on, let's say, a stovetop or something like that, maybe I'm burning a gas here. The exothermic reaction is happening in the coil, in the gas itself. That's delivering energy. Energy is sort of going into the surroundings. That's delivering energy into the water, providing this energy that liquids need to actually vaporize. As you end up increasing the energy here, the water particles also speed around faster as well. So not only is this energy used to do this phase change, it's also used to heat up the material as well. So endothermically, the heat is used to do both things. Now, the stronger the forces between particles, the higher the delta H vaporization. Right? So if we have hydrogen bonding as opposed to dipole-dipole forces, as opposed to just London forces here, if I have stronger attraction, it's going to make it even harder for us to actually breach this barrier here. So therefore, we're going to end up, even by the time you end up hitting equilibrium, you're not going to have that many particles. Because you have not as many particles, you had difficulty overcoming the attractive force, you will overall have a lower vapor pressure. When you have a lower vapor pressure, it's going to take even hotter temperatures before you have enough temperature for this whole thing to boil. So the conclusions out of here, we can say the higher the vapor pressure, basically the stronger the in-between forces, we have less gas particles at equilibrium. When you have less gas particles, we have lower vapor pressure. And lower vapor pressure means you even need even hotter temperatures in order to boil the entire sample. You need to heat it up even more, so you have those sort of correlations there. What are the major factors that actually affect this vapor pressure? Well, because we're dealing with boiling point, one feature is going to be definitely temperature. What temperature am I currently at? The other one here we alluded to already are the intermolecular forces, which sort of indirectly has to control the delta H vaporization. So for example, let's take methanol. Let's take methane. Methane is primary component natural gas. This guy here is a nonpolar molecule. If you remember from last year, nonpolar molecules here have the weakest force, only have very London forces, intermolecular forces to actually deal with. So in this case here, I may have liquid methane, right? But the particles don't actually attract each other very well. Because they don't attract each other very well, there's going to be a lot of particles in gas form. As you heat it up, not super hard to break up these intermolecular forces. We're going to end up having way more particles as you heat things up. As you have more particles, even if I'm in a closed system, that's going to then imply a bigger vapor pressure. So I'm plotting how much pressure there is. In this case here, maybe this is for CH4. At a low temperature, let's say maybe 20 degrees, just for argument's sake here. At 20 degrees, not a lot of those particles are in gas. They're exerting some sort of pressure. As we increase the temperature just a little bit, let's say 40 degrees here, because the intermolecular forces are so weak, you're going to have a lot more gaseous particles. And a lot more gaseous particles will end up pushing down on the surface a lot more frequently. The vapor pressure increases quite a bit quicker. Let's compare this methane case here. Let's compare it to chloromethane. So basically, I still take the same methane molecule, but I sub on a chlorine substitution instead. In this case here, we know we have a permanent dipole. This is a polar molecule. This one here actually has dipole-dipole forces. So the in-between attractions in this liquid here are a little bit stronger, right? So these ones here attract each other a little bit better. So again, at low temperatures here, we may have some vapor pressure there. But what you're going to need to do is you're going to need to increase the temperature a little bit more, right? Because the intermolecular forces are so strong, only the odd particles getting out. You need to increase the temperature quite a bit more before you manage to get more gas particles out, and when you have more gas particles, you're going to end up applying a bigger vapor pressure. So the chloromethane in contrast here, need more temperature for that vapor pressure to increase to the extent of, let's say, even in water's case here, similar to water, we have methanol. Methanol here has an H fighting with a very electronegative oxygen here. This is polar, but this one allows for H bonding. So H bonding is the strongest intermolecular force. Imagine my liquid really holds itself together really well. The enthalpy of vaporization is really high. You really don't get a lot of particles. At first, the vapor pressure is going to be really, really low. You need to increase the temperature even more dramatically, overcome those forces. As you overcome the intermolecular forces, you get more gas particles, and therefore this one here can steadily climb. So this one here is going to be methanol, CH3OH. Right? So let's just flesh this out a little bit here on the backside, and that'll be it. So what is this effect on temperature then? We studied intermolecular forces. How does temperature affect the vapor pressure? If you remember from our kinetics chapter, this is actually a kinetic energy distribution. This is called a Boltzmann distribution. At any given time, the temperature is proportional to the average kinetic energy of our particles. But just because it's an average doesn't mean all the particles are traveling at that speed. We actually have a lot of particles traveling at some medium speed. We have less and less particles traveling slower than it, less and less particles traveling faster than it. So we had, remember, an activation barrier. It was a chemical change in chapter 6. We're going to sort of use here, we're going to use this as the enthalpy of vaporization. You need to at least have this much kinetic energy, or else you can't breach the surface tension and you can't actually react. So in a similar way as we did before, it's only the really lucky, really fast moving particles that can actually collide. As we increase temperature earlier on, not only am I speeding up the particles so that I can potentially break these intermolecular forces, as I speed up the entire container, this curve here pushes over, and as it pushes over, what we end up seeing is at a hotter temperature, so this is at a higher temperature. At a higher temperature, we have more particles moving fast enough to breach the surface tension, to breach the intermolecular forces that keep that thin film on top. So the vapor pressure of a liquid is known to increase. The amount of pressure pushing down is increasing as the temperature increases. Let's think about that again. As you increase the temperature, you will undoubtedly have more gas particles. When these gas particles finally equilibrate here with the liquid, you're going to be applying more pressure. So temperature and vapor pressure are proportional to each other. At higher temperatures, the molecules of liquid will have more energy, more of them escape into the gas, so they apply more pressure. It's also possible that it's affected by chemical composition. So yes, chemical composition, we can talk about intermolecular forces, is it London force, is it dipole-dipole force as well? So just as summary here, as the chemical composition changes from one liquid to another, if I compare different species with each other, the intermolecular forces, the in-between forces actually matter. the in-between forces change as well. If the attractions increase, let's do our conclusion again, the enthalpy of vaporization increases. So it's a higher barrier to actually get over. We have less gas particles. That's really the way I think about it. If you have more gas particles, even by the time you're at equilibrium, you're going to have more vapor pressure. In this case here, with less gas particles, you have a lower vapor pressure. Right? So, by definition here, a liquid with a high vapor pressure means you have your liquid there, and at this temperature, whatever I'm at, it manages to vaporize really, really easily. In this case here, if it preferences the evaporation, we're going to call this a volatile material. It's something that becomes gas very, very easily. Covalent compounds are typically very volatile. So consider a couple molecules here. We have methane, methoxymethane, and ethanol. I'll draw these for you here to see if you can verify it. Methane, like we said, only London forces. So London only, really, really weak. So therefore, the boiling point is relatively low. The energy barrier is very low. Methoxymethane here is a compound here. It has an oxygen in between. This one here will have a permanent dipole. Remember, there's a bent geometry there. In that case there, the barrier is a little bit higher. Barrier is a little bit higher. The boiling point is a little bit higher. Takes even more temperature before the things break. When we get to ethanol. Ethanol is actually an isomer of this methoxymethane, but now we actually have hydrogen bonding. When we have hydrogen bonding, even higher barrier. So you need even hotter temperatures to end up boiling off. So you're going to even have higher temperatures before you get the high vapor pressures. So a couple of different points here. I wrote it for you a couple times already. In this case here, if I have stronger intermolecular forces, that leads to it being a higher enthalpy of vaporization. I would use as a sort of a side note here, higher enthalpy of vaporization means you have less gas particles at equilibrium. So less gas particles. And in that case there, if I have it so hard to actually form these gas particles here, we're going to have not only a lower vapor pressure, right? Less gas particles, they don't push down on the surface as strongly here. You're going to have even higher boiling points. You need to have even hotter temperatures for you to release enough gas particles for the whole sample to actually boil. Those are the things that are related to each other. Which ones are not related to each other here is the vapor pressure is not affected by the volume of liquid. So I can have a big beaker or a small beaker. The amount of vapor pressure at equilibrium is going to be constant. You can imagine, well, I have more liquid. Shouldn't I have more particles? But it's also spread out over a much larger area. So in that case, the volume of liquid doesn't matter. The volume of gas above the liquid, so sort of how much space you have above, we're not actually looking at all the room that we have. We're just looking at how many particles actually manage to escape. So in that case there, volume above the liquid. The number of particles in that gas space matters, but if I have a lid that's sort of right neck and neck with it, or if I make the container really, really tall, that doesn't interfere. We're going to wait till we hit equilibrium anyways. And then one other one that's important here is the surface area. I already alluded to it here. Yes, there's going to be more collisions, but that's spread out over a much larger surface. So the surface area of the liquid also doesn't matter. All right. So just a few other side notes. We had looked at a few industrial processes and then a little bit on vapor pressure. Tomorrow we'll come back and deal more with KC. Thanks, guys.